I want to, of course, acknowledge the fact that there are amazing champions in this space, and I think it's a privilege and an honor to be introduced by Gail. Her words, of course, are absolutely inspiring, and they do, of course, tell the story as it is, which I think is fantastic, because I think it's about time that we actually said, we've got the smarts, we've got the technology, we've got the desire, and most importantly, that stat, which is 96% of people here do connect with recycling. So I think in a way, we've got everything going for us. If we've got fantastic technologies, we've got manufacturers who are keen to incorporate end-of-life materials, complex materials into manufacturing high-performance products, then we've got the whole value chain covered. So really it is up to us now to make it happen, because we can't exactly say, oh, well, we don't know how to make high-value materials. We can actually show that we can produce high-value products, whether they are for building applications, for electronic applications, for manufacturing, industrial processing. So there are a whole range of different types of applications. And yes, electronic applications out of waste materials. A lot of these mixed plastics, let me just give you a simple example, actually have one thing in common. They all contain carbon. If they all contain carbon, the question is, why is carbon so useful and relevant? It is useful and relevant because carbon is actually a key material when it comes to making batteries. So you talk about energy storage and everything else that the general population is aware of. Well, remember, electrodes, cathodes and anodes in batteries make up more than half the weight of this product. If we want to be able to make batteries in Australia, we need ingredients, and for that matter, batteries anywhere else in the world. Some of the key components are the electrode materials. So I'm giving you that as an example just because a lot of people think about plastics as just that plastic material that we see with our eyes. But what I'm asking you to do now is, learn from Connie's outfit last night, the Superwoman or the Wonder Woman that she was last night, and think about X-rays. X-rays allow you to get down into the very molecular structure of a material, which means you can actually go down and say, what does plastic actually contain? If it contains carbon and hydrogen, why can't we actually use that carbon to manufacture parts and materials that we need for high-tech devices? And that's really part of the story and the journey that we're basically discovering at the Smart Center. It's about how you take different types of elements. So whether it's silicon coming from glass, whether it's zinc coming from those horrible disposable batteries, they're not that horrible. These elements, carbon, zinc, silicon, all of these elements that we're talking about, they actually have a fabulous purpose. It's just that we need to join the dots and connect them to manufacturing these types of high-performance materials. So you might say, well, but we really don't make batteries in Australia. So how are we going to start on this journey? Remember, whoever makes batteries anywhere in the world, whether it's Korea, Malaysia, whatever, they don't make all the components themselves, right? So it's like how Boeing is manufacturing across the world. You actually take different parts and components from different parts of the world and you put it together, which means we have the opportunity to take all the high-performance materials, like carbon, like metal oxides, and create the materials that we need to produce energy storage devices like batteries. So the work that we're doing in the Smart Center is really just that. Let's not just be so sort of, down on ourselves by saying, oh, well, really it's hard to recycle plastics because of the cross-contamination and mixtures and so on. Yes, that will be the case, but what they all have in common is carbon, hydrogen, and a lot of these elements that you can actually create high-performance materials. So you can actually create materials like activated carbon. You can actually create materials that are high conducting carbon products, and you can then use that as part of the supply chain to supply into a high-performance manufacturer like that of electronic devices. So that's really the journey that we have to be in. How do we contribute and be part of a global supply chain? But to be able to be part of a global supply chain, we can't just be sitting out there and collecting waste materials and, sorting and cleaning, all of that good stuff. But at some point, we've got to say, is there more value to be had? And of course, when you start to add more and more value to these high-performance materials, manufacturers of batteries and electronic devices, they need all of these products. So that's really part of the journey that we have to be in. And who knows, once you start to make electrodes, remember they are half the weight of a battery. Once you start to make electrodes, you can then start to make batteries. So you actually have got a tremendous opportunity right here in Australia to be part of that global supply chain. And these are the niche materials that we can actually start to produce. That's what knowledge economy should be all about. Using the science, using the technology, work in collaboration and partnership with businesses, with manufacturers. We've got manufacturing businesses who actually want to produce high quality carbon, but they depend on people like yourselves to be able to supply high quality input feedstock. So remember, then the question is, well, what's high quality input feedstock? It's about using that same X-ray vision, understanding XRD, for example, as a technology. You can understand molecular structures and you can understand how you then transform them into completely new products. And that's really where I'll show you some examples. How do you actually take materials like waste glass and create high performance building products from that? You know, how do you make that journey happen? It's not just about saying, well, you know, let's just put it somewhere where no one will see it and let's not worry about it, but it's about accepting the fact that glass contains highly valuable silica. Silica is an oxide of silicon. So remember, you need silicon for making so many important electronic devices. So we've shown that you can produce silicon carbide. The silicon comes from glass, the carbon in the carbide comes from plastics. So if you actually combine the two and you get silicon carbide, this is a very expensive feedstock for those who want to produce high performance materials. So why should we just see our glass and plastics as a problematic mixture? Why can't we actually see that transformation into silicon carbide, and therefore that's where the value chain comes from? So that's really what the journey should be about, is the discovery through technology. And this is where, of course, science plays such an important role. Because first and foremost, scientifically, you've got to prove that it's possible. You can't just sort of sit there and imagine that this will happen. Yes, imagination and thought bubbles, as I often do, speak to myself, is an important starting point of the journey. But I think it is more than that. It's really about the fact that thermodynamics, kinetics, and understanding the transformation of materials is where we're going to have to go if we want to be able to produce high-performance devices, our phones, our computers, our batteries. All of these types of materials require high-performance materials. So we talk about rare earths, and everyone sort of is aware of rare earths, and oh, you know, all of it's coming from, a large part of it's coming from China and so on. They've got the reserves. They know how to make it. Well, guess what? We're sitting on reserves too. It's called electronic waste. So rare earth oxides is a big part of our hard drives, for instance. So why don't we actually look at generating new rare earth oxides, REOs, neodymium oxide, and so on, from our hard drives, from magnets? All of these types of solutions scientifically are possible. It's about whether we have the desire to be really smart about these types of solutions. So what we do at the Smart Center is, of course, develop new technologies, understand recycling and their transformation, and of course, working with our manufacturing partners, understand how to actually produce these products of the right quality. Remember, in these niche materials, it's not about mass production, it's about niche, high-quality materials, and we've got the smarts to actually do it. So innovation is really very much, for me, it's about doing things a lot better. So ultimately, at the end of the day, we can deliver solutions that make lives better for people. So everything that Gail referred to earlier about creating jobs, it's about delivering value-added solutions so that we can actually have advanced technologies and the all-important competitive advantage for businesses. That is important. How are you going to compete in a global marketplace if you're just basically pushing out low-value materials? So you need to be able to push out high-value products that the world actually needs. This is why when we talk about, you know, battery storage device, energy storage devices like batteries and so on. So the journey of innovation for us at UNSW has been very much about understanding the big picture, all the things that I've told you so far, about understanding what the future challenges are going to be. If we are going to make energy storage more and more affordable, well, it's like photovoltaics, like solar cells. You know, how do you actually make it more affordable? Is understanding the materials and the technology that goes into making PV cells. In the same way, energy storage is going to become more and more affordable if you can actually understand what materials the manufacturer needs. And if we can be part of that supply chain, that's fantastic. So it's about delivering economic benefits and value to businesses. So that's a little bit of a big picture overview. What you can see there in the pink is really different types of input materials. So whether it's about different plastics and tires, they're all polymers, wood, textiles, packaging materials, of course, C&D, C&I, you know all of that. And of course, with electronic waste, there's no end to it. All kinds of valuable metallics. So you can see in terms of the outputs, everything around in green circles shows the kinds of materials that we are actually manufacturing. Some on that journey have been commercialized, and some are on that journey to be commercialized. So rare earths is a good example. It's a difficult problem. Nobody in the world has cracked it. And you know, if we are going to be the first in the world, we've got to be absolutely sure that the science works. So I'm happy to tell you that a lot of the new scientific discovery over the last year or two have actually now been published in world-leading journals. Why is that important? That's important because it shows that Australia can be smart when it comes to new science. We don't always have to look at Europe and America and go, well, they know how to do science. We can be really clever about it. Of course, all of this is funded federally through the Australian Research Council. So that's an important acknowledgement that through the journey of world-leading science, we've actually arrived at a lot of these solutions that show how do you actually produce rare earth oxides from hard drives, for instance. How do you actually produce filaments? We're making plastic filaments out of 100% recycled e-waste. Why don't we actually create those and use it, not just in Australia, but let's actually export these plastic filaments. Let's actually export rare earth oxides and, of course, create that much more value. What else is out there? We've talked about carbon. And, of course, don't forget metallic alloys. There's a lot of metals, of course, in circuit boards, for instance, and the list goes on in terms of copper, nickel, tin. Whether you're talking about base metals. Remember, if the world is going to become more and more electrified, this electrification journey means we need metallics like copper for our cars, for our buildings, for everything around us. Infrastructure is no longer just the building blocks that we're used to. Infrastructure is very much about the embedded electronics. Well, where is that going to come from? Can we imagine in the future that every time we break something down, a small part in our car or in our sensors in the buildings, we're going to have to depend on somebody else telling us how to fix it, or how to refurbish it, how to retrofit it? Why can't we do that ourselves? So that's the point. Infrastructure can be set up. We can make products. But I think the important part of manufacturing also has to be about servicing, because a lot of these infrastructure around us is going to last for a long, long time. It's how do we actually service it? So we need all of these resources, whether they are metallics or whether they are oxides, rare earths, carbons, all of these important materials that become part of the value chain is going to be important. So really it's about creating new opportunities, and I'll take you through a little bit of highlights as to what these new opportunities are. We've shown some of them are possible, and why are we doing it? Quite simply, traditional recycling of always converting waste plastics to plastics doesn't necessarily work all the time. And that's why we need to tap into where the money is. Quite simply, UNEP has shown that electronic waste, as an example there in front of you, has got billions of dollars worth of embedded resources. We need to be part of that value chain. I'll skip through a lot of this information. We're sitting on a lot of electronic waste in Australia. You all know this better than I do. There's an opportunity that we should be tapping into. I'm going to, of course, skip through some of these slides. A lot of our work that has been proven now through our own microfactories has shown that you can achieve a lot of these outputs. Remember, these are niche, high-value alloys. You don't need large, mass-scale production. What you need is the ability to show that it can be done on a micro scale where you can have distributed manufacturing. So you can actually carry out that transformation wherever waste is being stockpiled. So those are really parts of what we're trying to do as part of the vision in the Smart Center. So I'm going to skip through some of these slides in just a moment, if it's going to just quickly fast forward through. again, I'll skip through just in the interest of time, but you all know what kind of e-waste plastics I'm talking about, whether they come from printer bodies and all the other hardware. The Smart Center's goal is very much about creating value-added products. So I'm going to show you one video if it plays in just a moment. I might get to the next slide and just see, because I think this is not responding that easily. So this is what the 3D printer is doing. It's actually printing out products from e-waste plastics. So remember what we've done here. We've created filaments. These filaments, which are basically produced, you can see they're out of e-waste plastics. We've then converted those filaments using 3D printing into finished products. So that's really what we're trying to do as an example sorry, I'm going to try to just click through the next slide. That's the next one. And I'll just skip through some of these just because we're running out of time. A lot of the work that we're doing, of course, also has got implications, like I was talking about, producing oxides, rare earths, metallics. All these videos you're seeing are transformation at high temperatures. So it means that for manufacturers, it's possible to now create a lot of these types of solutions without necessarily depending on smelters that operate at high temperatures. I think I might have to click through that quickly. So this is really an example there that I've shown you on the right-hand side of an alloy, iron silicon alloy, which we can produce in partnership, of course, with our manufacturing partners. Okay, I'm going to just mention very quickly the point about going through this journey of reduce, reuse, recycle is to really just leave you with 1/4 R, the 4th R around reform. How do you actually reform these materials? So what this science is really all about is enabling that reform to actually take place so that you can create high-value materials. That's an example of metallic alloys, which you can see on the right-hand side. Circuit boards being transformed into high-value alloys. So there are alloys that contain copper, tin, and so on. So that's really an example of what can indeed be produced from circuit boards right here locally. Remember, a lot of these types of alloys are bought and sold in the marketplace for thousands of dollars a ton. So we're talking about the fact that these are expensive, highly valuable metallic alloys, and that's the reason why it's far more important to produce value-added products. Some of the other examples for building applications, panels, whether they're made out of wood, glass, textiles, and I'll just skip through all of this very quickly just to show you a few pictures, whether they are acoustic panels, thermal insulation panels. A lot of these have been made by taking blends of different types of waste resources, textiles, wood, of course, glass as well. So it really just comes down to what kind of application you want, whether it's about acoustics, whether it's about structural panels for flooring, walling, and so on. So the engineering of all of this comes down to how these materials bond together at the molecular level. So it's not just about gluing it together, but really about saying, can we actually create bonding at the molecular level to allow some of these smart products to be manufactured. So just to sort of finish off, and I'm going to try and get to the final slide. Some of these properties are there, modulus of rupture, and look, I won't get into the details. The scientific papers explain that if anyone's interested in looking at it, whether it's for general purpose applications, load bearing, heavy duty applications. A lot of those publications are available in the public domain. And I'm going to quickly get to some of the other very interesting looking products. So all of these are really just to be able to show that waste resources can actually be transformed and reformed into valuable materials. And I'm going to probably stop there because I'm sure Gail wants me to finish up. So look, thank you very much for your interest and for the invitation to be here. Thank you.